Warm welcome also from my side. Today I would like to talk about cinder-based additive manufacturing and metal injection molding. This will take approximately 30 to 40 minutes. So here's a quote from a McKinsey report back in 2014 about the factory of the future. If you only remember two technologies, they should be additive manufacturing and metal injection molding. So both technologies do have huge potential or huge capabilities for the production of complex metal parts with respect to lightweight construction, freedom of design, and the reduction of joining operations or assembly operations. So starting point for cinder-based AM and MIM is always a metal powder and a binder. The binder is only necessary for shaping. It keeps the metal particles in place. The main difference in the production route of cinder-based AM and MIM is the way how the green parts are shaped. So for the case of additive manufacturing, the part is built up layer by layer. We will see in the next slides that there are many different technologies and all have their own way to shape the parts, but it's always a layer-wise construction. And in case of MIM, a feedstock, which is actually a compound of the metal pounder and polymers, is injected into a mold tool. So after shaping, the green parts needs to be debinded. Depending on the binder system that is used, one can choose between solvent, catalytic, and or thermal debinding. So actually the base polymer is removed during that debinding step. Then the brown part is transferred into our sintering furnace, in which we do a thermal debinding and the sintering to consolidate the metal powder to a fully metallic and dense part. Today, I will give you an overview of 5 different cinder-based AM technologies. Of course, there are some more, but these 5 are actually the technologies we took our focus on. So first, material extrusion. I'm sure, or I guess, most of you in the audience already know that technologies. It's well known for plastic 3D printing. The second is binder jetting, which is already established in some MIM companies, and they can offer a prototype or a small series production to their customers. And the other 3 technologies, stereolithography, cold metal fusion, and Smallchat, are pretty new technologies, but they offer high potential and are very promising. First, I would like to start with material extrusion. A filament, which is a compound of a metal powder and a binder, is extruded and plasticized in the print head. There are also some printers available that use granules, so conventional MIM feedstock instead of a filament. The extruded filament is typically applied on the build plate in a meandering pattern, and the part is built up layer by layer. So support structures are necessary for this technology in case of printing overhangs or holes like indicated in that sketch here. Material extrusion is a low-cost technology. Basically, the printers are relatively cheap, but the material cost is high and the productivity is low. The filament typically obtains a solid loading of 60 volume%. Depending on the binder system, the parts can be debinded in a solvent or a catalytic debinding is performed. Then the brown parts are put into the sintering furnace, in which the backbone binder is burned off and the part is sintered. During sintering, due to the densification of the metal powder, the part shrinks You can see it in the pictures here, the dimensional change of a green part to a sintered part. The sintering shrinkage for this technology is roughly 15 to 20%, but you need to keep in mind that the sintering shrinkage is anisotropic in this case, and shrinkage in Z direction is a bit higher as for X and Y direction. You can also see that the surface quality is quite poor. The extruded filaments are still visible after sintering. Okay, the next printing technology is binder jetting. The basic principle of binder jetting is similar to SLM, so laser powder bed fusion. But instead of using a laser who fuses the metal particles together, a binder is used to connect the metal particles. After spreading a thin layer of the powder, the printhead moves over the powder bed and locally applies a liquid binder which connects the powder particles. A main characteristic of this technology is that the green parts obtain a very low binder content. It's only 1 to 2 weight% of binder. The rest of the green part is porous actually after printing. You don't need to consider support structures during printing since the powder bed supports the printed green part. And the printing process is pretty efficient due to the possibility of nesting. After printing, the build box is removed from the printer and put into a curing oven. So here the binder is cured to improve the green strength. This is crucial because the next step is depowdering, which is a manual process. Here the loose powder is removed from the printed parts, from the print bed. And this is done by using brushes, compressed air, or suction pipes. So you can imagine if you have a filigree part and it's pretty fragile, you need to handle it with care during this depowdering step. Then the parts go into the sintering furnace for thermal debinding and sintering. The shrinkage here is approximately 20%. Again, with a higher shrinkage in Z direction, and high densities well above 96% can be achieved with this technology, and the surface quality is quite good. Stereolithography is well known for plastic and ceramic AM, but it's also capable of producing metal parts. So here the raw material is a mixture of a photopolymer and a metal powder. At room temperature, this feedstock has texture like butter. So the blade is heated and the blade liquefies the feedstock, and a thin layer of that feedstock can be applied in the build box. So then this thin layer is exposed to UV light. In the sketch on the upper right, you can see a sketch of the mechanism. So first you have a randomly distributed mixture of your metal powder and monomers. The exposure to UV light leads to polymerization or cross-linking of the polymers. So actually the part is cured layer by layer. So you don't need a support structure for this technology as well. It's supported by the surrounding feedstock. Nesting is also possible here, so you can effectively or efficiently use your build volume. And this method is best suited for small and filigree parts, and you can print fine details. So after printing, that butter-like block is removed from the printer and is heated by an infrared lamp or in an oven to melt the excess, the uncured material off. And typically the parts are then cleaned in a solvent. The solid loading of the feedstock is roughly 60%, which results in a sintering shrinkage of 16 to 20%. In this case, or for this technology, due to the fact that you use photopolymer as a binder, you can only apply thermal debinding. Thermal debinding is pretty ineffective, so you need longer sintering cycles compared to the other technologies or MIM. Yeah, as you can see on the pictures on the lower right, yeah, fine details can be printed and the surface quality is pretty good. Cold metal fusion is our next technology. It's a technology that uses conventional SLS, so selective laser sintering printers, known from plastic 3D printing. Here, the raw material is actually a feedstock, which is like a powder. It's the particles of the feedstock do have a size about 100 microns. So first, a thin layer of that feedstock is applied, and then a laser locally melts the binder. So upon cooling, the powder particles are fused together, and the part can be built up layer by layer. Support structures are not necessary since the printed part is supported by the surrounding feedstock. After printing, the green parts need to be depowdered. In comparison to binder jetting, the green parts from cold metal fusion are much more robust. The binder content is much higher. And so the depowdering is not as crucial as for binder jetting. Besides using compressed air, you can use also a water jet. Furthermore, the green parts can be processed. For example, threading or other milling operations can be performed on these green parts. Then a solvent debinding is performed to remove the base polymer, and the parts are sintered. Here the sintering shrinkage is pretty low, approximately 13%. And high densities can be achieved with this technology. Our last sinter-based AM technology for today is Smallchat. This technology differs from the other technologies in the way that first a layer of a mold is printed, and then a metal paste is placed in the printed mold. So the mold is actually a negative of the part geometry. So then a drying and hardening step is performed, and the sequence of printing the mold, filling it with the metal paste, and the hardening is repeated layer by layer until the green part has finished. The green part is supported by the mold, so support structures are not required, and nesting is also possible in order to use as much of the build volume as possible. After printing, the green parts need to be demolded, so the whole block is put into an oven, and the wax-like mold material is melted off. The green parts also obtain high green strength, high stability, so post-processing operations can be done on the green parts as well. Sintering shrinkage is typically around 14%, and high densities can be achieved with this technology. So now I finished my overview of sinter-based AM, and now I will start to give you an introduction into metal injection molding. So MIM basically consists of 4 process steps. That is the feedstock production, the injection molding, debinding, and sintering. So after injection molding, the green part consists roughly of 90% weight metal powder and 10 weight % of polymer. Then the pre-debinding is performed, where the base polymer is removed. Afterwards, we will get the brown part, which now only consists of roughly 2 weight % of the backbone binder, which is necessary for shape retention. And then this brown part is transferred into our sintering furnace for thermal debinding and sintering. So starting material is a feedstock, which is a compound of metal powder and 2 or 3 polymers and some additives. The feedstock is designed for an optimal flow behavior in order to promote a proper mold filling. The organic binder in the feedstock is only necessary for shaping to guarantee a flowability of your metal powder. After sintering, the pot is free from organic carbon and is fully metallic. Injection molding is performed on conventional injection molding machines known from plastic injection molding. The feedstock is plasticized in the extruder here and molten and then injected into the cavity of our mold tool. The shaping is actually the big difference between cinder-based AM and MIM. So MIM always requires a mold tool, whereas AM is a toolless technology. The mold tool consists of several components, runners and gates, ejector pins, slides, and of course the cavities. So typically the tool or the mold tool is made of steel. Here you can see an example of a mold tool with 8 cavities. So you can produce 8 parts with 1 shot. So I'm sure you can imagine, depending on the part geometry, on the complexity of the part, the mold tool manufacturing can be expensive and time consuming. That is why MIM is typically reasonable for medium, economically reasonable for medium to large scale production. A quite elegant alternative for prototypes or small series production is the use of 3D printed plastic tool inserts. So on the lower right, you can see 3D printed plastic tool insert. We're currently working on this and doing trials here. Using a mold tool leads to some design guidelines for MIM. So MIM is ideally suited for small and light parts. In general, the smaller the parts, the more cavities can be realized in the mold tool. Additionally, better tolerances can be achieved for smaller parts after sintering. A constant wall thickness is also preferred to prevent material accumulation. Material accumulation is crucial because it can lead to cavities. And you don't want to have cavities in your material. The cavities exist due to the thermal shrinkage of the feedstock. So you really want to prevent material accumulations. Not least because due to the fact that the material accumulations can also lead to sintering distortion. Round edges enhance proper mold filling, so the flowability is better, and draft angles are necessary for demolding. Of course, there are some ways to overcome design guidelines or the restrictions of MIM due to using a mold tool. The first example here shows a part which has several of these tubes These tubes are not fillable due to the high aspect ratio and the thin wall thickness. But what we can do is cocentering. So what we actually did, we produced the green part without these tubes. We bought steel tubes and we inserted them into our green part and joined them while sintering. So afterwards, we had our sintered part that looks like it should. The second example is a part with an undercut, which is not demoldable. In this example, we split the part geometry into two parts, and you can't even, so we joined them, this star and the nozzle in the green state, put them into the sintering furnace, and afterwards we got one component, and you can't even see an interface between these two parts. In contrast, additive manufacturing gives you a higher degree of design freedom because you don't need a tooling. So undercuts are usually not a big problem for most of the AM technologies. Another features like cooling channels can be realized quite easy. However, some guidelines also apply for AM as well. Constant wall thickness is recommended to promote homogeneous sintering shrinkage, and round edges are also preferred to reduce stress concentration. Both technologies, AM and MIM, have in common that the parts need to be sintered after shaping. Sintering is essential to transform the green parts into a fully metallic part. So basically, the reduction of surface energy and diffusion processes are the main driving forces for the densification of the metal powder of the part. Usually a two-stage sintering is performed. The first temperature plateau is for thermal debinding. And the second sintering temperature is, or the second plateau is the sintering temperature, which is actually close to the melting temperature of the material. While sintering, the parts are subjected to creep and friction due to the sintering shrinkage. This must be considered for part design. So shaping green parts by AM or MIM is usually not a big issue, but you need to get your part through the furnace, through the sintering furnace. So sintering is actually a challenge. That is why you should keep in mind some design guidelines for sintering of AM and MIM parts. So a flat contact surface is preferred to prevent distortion. So gravity and creep will deform your part if you don't have flat contact surfaces. Furthermore, it might be helpful to add support structures. So you can surely imagine that this balcony over here would hang down after sintering without that support leg indicated in red down here. So of course, it is designed in a way that the support structure can be removed after sintering in an easy way. So this one here has a notch and it can easily be cut off after sintering. Another option is the incorporation of reinforcement structures. So the part itself is stiffer and sintering distortion can be avoided. So sintering requires a lot of know-how and experience. But anyway, AM is helpful in that context as well. So AM is a helpful tool to print different variants with different support structures, and then best part geometry can be determined in terms of sintering distortion. So prior to mold tool construction, different geometries can be tested and evaluated with respect to their deformation. Okay, now it's time for a comparison of the different technologies. So first I would like to start with the part size and the production volume. So MIM, as I mentioned earlier, is suitable for medium to large scale production. Part size typically ranges between a few millimeters up to 100 millimeters. But usually as part size increases, the production volume decreases. And this is also true for most AM technologies. Binder jetting and Smallchat are suitable for low to medium production volumes. Smallchat covers more or less the same part size range as MIM, whereas binder jetting is better suited for medium or low or small to medium part sizes. Stereolithography is ideally suited for small parts to medium parts up to a quantity of a few hundred parts. And cold metal fusion and material extrusion are better suited for medium to large parts. And here 100 millimeters is not the end, so you can go much farther. 200 and 300 millimeters are also possible with this technologies. So with regard to part complexity, material extrusion is far behind the other technologies. MIM is capable of producing complex metal parts, but as I showed you on previous slides, there are some guidelines or restrictions that might be overcome. But anyway, there are some restrictions, and you have a higher degree of freedom for Smallchat, cold metal fusion, stereolithography, and binder jetting. Here's the material portfolio that is currently available for each technology. Since MIM is the most established and oldest method, it offers the broadest material portfolio: stainless steels, low alloy steels, tool steels, super alloys, titanium and titanium alloys, and copper, as well as special alloys or materials like ceramides or neodymium iron boron can be processed by MIM. These special alloys are, by the way, a topic of our 4th webinar. So most of the material extrusion systems offer stainless steel and sometimes copper. If you use a system that is suitable for the processing of granules, so the conventional MIM feedstock, the same materials are available as for MIM. Binder jetting also offers a quite broad material portfolio, and many materials are under development. Stainless steel and titanium are available for stereolithography, but they're not yet officially qualified. Cold metal fusion offers stainless steel super alloys and titanium, and other materials are also under development, and stainless steels are available for Smallchat, and many other materials and alloys are tested and under development. The next criteria is the capability of shaping fine details like thin walls or small holes. Again, material extrusion is far behind the other technologies. Cold metal fusion is better suited in this regard, but it's still behind MIM, Smallchat, binder jetting, and stereolithography, which probably gives you the highest level of detail and has a slight advantage here. The last point is surface quality. In general, parts made by AM have a lower surface quality as MIM due to their nature of shaping. It's a layer-wise construction. Anyhow, stereolithography, Smallchat and binder chatting are pretty close together and obtain a quite good surface quality. Cold metal fusion leads to a bit rougher surface, and the surface quality of material extrusion is quite poor. I would like to conclude my talk. I hope I could show you that cinder-based AM and MIM is capable of producing complex metal parts. In most cases, shaping is not a problem. Sintering is a challenge. So it might be useful to adjust your part design with respect to sintering distortion. There's not the one and only technology that is always used for any application. All of these technologies have their pros and cons. So you need to choose carefully which technology is applicable for your requirements. In our opinion, cinder-based AM and MIM are not competing processes, but they are complementary to each other. So AM expands the limit of MIM with respect to part volume and vice versa. And additionally, you can realize part geometries that aren't possible in MIM using additive manufacturing. I'm at the end of my talk. I would like to thank you for your attention. And now it's time for Q&A.